Thank you for checking out our on-demand webinar. We wanted to take a different approach for this presentation. Microtrack, the global pioneer of particle characterization solutions, is a proud member of the Nikiso group of companies. This webinar focuses on our sister company, BEL, the Japanese market leader in adsorption technology. BEL was founded by Professor Nanu and Dr. Kazu Nakai in 1988. Since 2013, Microtrack has been distributing BEL products outside of Japan. Now, I would like to hand it over to Dr. Phil Plants.
Thank you, Jason, and welcome to all of you to our webinar on force coordination polymers and metal organic frameworks. The whole concept here is to look into the structure of these various materials. This is somewhat of an innovative approach to understanding the structural changes that can occur when MOFs or PCPs are exposed to adsorption phenomena, but also I'm going to talk a little bit about changes that can occur with MFI zeolites. Much of this information is according to research and data and development of Dr. Kitagawa at Kyoto University. Now, the types of compounds we're talking about is a combination of metal ions and ligands, which leads to a cage-like structure. And this is developed into a three-dimensional structure as the assembly occurs. These are called porous coordination polymers or metal organic frameworks. The idea here is that the pore size that develops within these structures, the ligand plus the metal ion, can be developed based upon the ligand and the metal ion present. There's a regularity that develops as these assemblies come into a full assembly structure. Now, these can lead to a very flexible framework, and we'll talk about this in just a second. But also, this framework can be very, very rigid, and we're going to talk about the flexibility and rigidity of these structures and the information that has been developed over a period of time. Also, these structures can lead to true chemical bonding and surface modifications. As Jason alluded to, there are a number of applications for these types of structures. One of them is storage. Here we can look at energy considerations, fuel cell development, and carbon dioxide capture when we're thinking in terms of climate change and those types of issues. We can also look at separation of various types of gases, and this becomes a very selective process based upon the structure and the pore size of this cage-like structure. We can also develop structures that have catalytic activity, and this can be very valuable in terms of cracking or looking at exhaust gases, such as what you might find in a catalytic converter in automobiles. We can also develop structures where polymerization can be controlled and develop the products from the catalytic structures to develop various types of polymers. But also, these types of structures can be customized to achieve a certain structure-function relationship. So for what we're actually talking about is developing specificity of chemical reactions and separation of compounds. Now, in this particular slide, we're looking at an isotherm, a benzene adsorption on a structure named CPL-2. Now, please note that at present, IUPAC is in the process of assigning nomenclature rules for these structures. So these types of structural names are based upon the researcher that's involved. Now, the first thing that I'm showing here is an adsorption isotherm, and on the y-axis, we're looking at the amount adsorbed as a function of the relative pressure. Now, please note that this is a linear axis. This is a linear scale. And when we look at the adsorption isotherm, as we follow through here, we'll note that even at zero relative pressure, there is adsorption occurring. But when one looks much more closely at this particular area by looking at the logarithmic scale of the relative pressure, there really is an indication that adsorption of the benzene molecules into this particular MOF structure is actually occurring. It's just not as well resolved by a linear scale as compared to this logarithmic scale. And this is showing a one-step adsorption isotherm, which is typical of a type 1 adsorption isotherm. Each point is developed at an equilibrium relative pressure, as normally performed with development of an isotherm. The isotherm indicates that the adsorption characteristics of the MOF for benzene. The one-step isotherm indicates a single MOF structure has developed. If there were more than one step, then it would indicate structural changes. And I'm going to show you some data in just a little while where the value of simultaneous MOF structure XRD analysis in combination with adsorption becomes very, very valuable to understand this process. Now, in the next slide, we're going to look at the XRD analysis that was obtained through this process. Now, this is the XRD information, and here we see the intensity as a function of angle of diffraction. And what we see here are three different spectra. The first spectra is as the material is synthesized and water is part of the structure, and it takes on its own characteristic spectra. But then if the water is removed and only the MOF is present, then we have a slight change in this structural information that's being obtained by X-ray diffraction. But then in the presence of benzene, we start to see some significant changes in the spectra that are very, very interesting. Now, what we've done is focused on this particular area here at this lower angle, and that's being presented over here, and it's kind of zoomed in on and exploded somewhat. Now, with the water as a guest or part of the structure of the compound, we see that very first peak having an intensity that looks somewhat like this. And then we have also the structural information when there is no water present, and this is the pure nascent compound. And this is shown here as having no structural change. And this is the basic structure where we're starting. And this takes on the structure of a square pyramidal structure. And this shows the atomic lineup, but this also shows below this, without the guest, this shows the spatial considerations of these molecules and atomic structure. But also, when we take a look closer at the MOF after exposure to benzene, there is a structural change that occurs according to the XRD analysis, where we're using a Rietveld analysis on the powder. And we undergo a structural change from the square pyramidal to a square planar, and the structure has changed as a result of the benzene molecule being adsorbed into the structure. So we can start to identify information about structure as adsorption occurs, but usually this is done only before the adsorption occurs, as we are doing here, and then after the adsorption has occurred. But there are many steps that can occur along this adsorption process that are left behind and not available. Now, as the adsorption proceeds, the pore structure may change, and we just saw some evidence of that. So there's a need to observe changes to the isotherm at the start, where there's no adsorption, during the entire adsorption process, and at the end, where saturation occurs. Previously, it was only possible to have XRD data before and at the end of the adsorption process. So there's no way to correlate kinetics of structural changes to specific adsorption conditions. Now, consider that at any step in the adsorption process, it is not possible to maintain the equilibrium state at a relative pressure by trying to stop the adsorption, take the sample to XRD, make that measurement, and then go back to the adsorption to the surface area analyzer and resume the adsorption experiment. Thus, only data at the start and at the end of the adsorption process was previously available. It could be stopped and then get the XRD data, but then you would have to start the adsorption process over, and it became an extremely time-consuming, tedious way of performing the analysis. And there could be changes and other things that could happen during the transfer. So it was impossible to have knowledge of structural information and the effect of adsorption at various equilibrium states because no XRD data was available during the entire adsorption process. So to gain knowledge of the structural changes during the entire adsorption process, it's important to obtain information in situ and during the adsorption process simultaneously at each relative pressure of exposure to gases or other chemicals. Now the basic system we're talking about here is that we have XRD equipment, we have gas adsorption equipment, and this is the BEL-MAX system, plus computer capability to operate the different instruments. Now, much of this work is based upon a reference that I'm showing below here, authored by Dr. Matsuda and Dr. Kitagawa. And if you need this reference, please let Jason know by email or phone call, and we will be glad to provide this to you so that you don't have to write this down feverishly. Now, the way the XRD measurement is made is that we have an X-ray source, and that is directed at the sample, and then the diffraction occurs, and then the diffraction information is available to a detector. Now, to allow for surface area and porosity measurements, it's necessary to have a shroud or an isolated capability around the sample cell area. The sample resides here, but to allow surface area measurements to be made simultaneously, it's necessary to isolate this entire area. And to do that, it requires certain types of windows made of beryllium that allows the transfer of the X radiation to the sample, and then as the diffraction occurs, then the diffracted information must be made available to the detector. So there are beryllium windows on either side of this contained sample. Now, obviously, there has some cryogenics involved with this entire system because we're going to be looking at surface area measurement. Now, to do that, keep in mind a couple of things. The sample stays in place. There is no removing of the sample or anything of that nature. The very first thing that happens in these processes that I'm going to be showing you in just a second, some actual data, is that first the adsorption equilibrium is achieved at each relative pressure. Then XRD measurements are performed at that specific relative pressure. So we have basically a simultaneous measurement of the porosity, which can give us information that structural changes may be occurring, but also we get the XRD information that analyzes the sample for any structural changes. Now, let us look deeper into the value of this simultaneous XRD adsorption for looking at structural elucidation. One of the things we're going to be talking about here is synthesis of what are called 2- and 3-fold interpenetrated compounds. And again, this reference will go into much more detail than I possibly can during this short talk that I'm giving you. Data in subsequent slides will show some the value of the simultaneous measurements and the value of being able to identify structural changes that can be occurring. But what we're basically talking about is taking something like this compound, zinc nitrate, and we mix it with BTDC plus bipyridine. And we're going to look at this under two different conditions, with where the sample and the reactions are conducted in dimethylformamide in the presence of benzene. And this will develop what's called a two-fold interpenetrated structure. I'll explain what this means and what the three-fold interpenetrated structure means also. But also exposure and synthesis in DMF at 120 degrees C is above, but without benzene produces what's called a three-fold interpenetrated structure. This will give rise to a flexible structure. This gives rise to a rigid structure that I referred to previously, but I'll go into that in a little bit more detail. Now, this is the concept of interpenetration. This leads to two-fold and three-fold concepts. Now, this is using the same metal ion ligand. Now, what we're looking at, and the best example of what we mean by interpenetration or intertwining, is that if we look at this where we have twine, but if you'll notice, if you can follow my cursor, you'll notice that this red piece of twine goes under this white piece, and then over this white piece, and then under the blue, over the yellow, under the blue, over the orange, under the white, over the orange, etc. And then if we look at another piece of twine, we'll notice that there's also that same type of thing occurring. But if we look at the blue, then we start to see a different type of pattern. So this is the intertwining. So it's in terms of molecular structure, these are kind of all, I hate to use the term mixed up, but it is the structure that develops what is called the two-fold MOF, or a double MOF. Now, if we look at this in terms of the flexible two-fold structure, the structure is not crowded, and space allows for structural changes. And it turns out that the pore size for the double flexible MOF has a pore size of about 6.8 by 6.8 angstroms squared. But then, if we go to the threefold, where the interpenetration is much greater, the whole structure becomes fairly crowded, and there's really no space, and it cannot undergo structural changes. So if we look in terms of this type of structure, this representation of twofold, and compare it to the threefold, we see that the pores and the void areas inside the system is much, much less, and at least the pore sizes that are, I'm going to say, on the order of about half of what we find with the flexible structure. So we can start to see some special and interesting structural developments from the XRD information. Now let's go back to the whole concept of adsorption and desorption isotherm. And in this case, we're going to look at carbon dioxide on a two-fold structure at 195 K. Now again, we'll look at the classical amount of adsorption as a function of relative pressure. And you'll notice at the beginning, we would be able to obtain this information. And classically, over history, the next step would be to have adsorption stopped somewhere along this process, and possibly at the end of adsorption and full saturation, we would have a point here and a point here, but all this information here is lost. But it could be obtained, but it would mean that there would have to be a number of measurements made that are not automatic, and also each one of those would have to be subjected to a separate XRD measurement, which makes the whole measurement system very complex, and there's always the possibility of some kind of changes occurring which would confuse the data and the interpretation. But using this integrated system of adsorption, desorption, and XRD, we can follow what's happening along this entire adsorption process. And you'll notice this is a two-step process. And so right away there's some indication that there's some major structural changes occurring, as I mentioned before. But down here at this very first point, I have a representation of the XRD. And please take note of some of these peaks. So as we go forward, and adsorption is occurring, and remember, this looks like there's really no change in the adsorption at virtually at zero partial pressure, relative pressure. But as I showed you before, with a log representation of this, there is actually a very slight change in the relative pressure leading to adsorption within the structure. And we're seeing that starting to occur here because there are changes already occurring during the early parts of the isotherm development. And we can see these changes starting to occur. And I'm going to go through this a little bit stepwise. And as we get further along in the isotherm, we start to see that there are major changes occurring here and throughout this. This major peak now is reduced, and then we're starting to see some shifts along here. But then as we go further along, where 4 molecules are in the pores, and they're becoming saturated with as many those 4 molecules, but then it starts to accept more molecules, and in this case we're going to 5 molecules, and we can see changes as we're moving from this situation where there are maybe 3 molecules in each pore to 4 molecules, and now we've got 5, and we continue to see changes in the XRD information based upon the spectrum. And then we can continue the process, and as more and more CO2 molecules are being accepted into the cage-like structure of the MOF, and then we continue further, and we start to see even more changes that are occurring as the relative pressure is starting to achieve saturation, and more molecules along the line here. We're starting to approach somewhere between 6 and 8 molecules per pore. And then finally, as we reach saturation, we have 8 molecules located inside the pores per 8 molecules of CO2 per pore. So we're able to track everything that's happening and the structural changes that are occurring throughout the entire process of adsorption, and we can now start to get kinetic information as to these changes and what can be expected. So now the XRD data is now available during the entire adsorption process. At each adsorption equilibrium, XRD data are obtained. Previously, again, the only thing that would be obtained would be to take the sample and then expose it to a chemical, CO2 or benzene or something else, and then somewhere along here take one point, and then the whole process would have to be repeated time and time again. And with this type of instrumentation and the integration of adsorption with XRD allows this all to occur automatically with some controls imparted in the software. Now I want to shift the emphasis just for a second because we want to look at something kind of interesting that was discovered by Dr. Kazuyuki Nakai at BEL. There is a pore structure change for MFI zeolite. If you're not familiar with MFI zeolite, it's a silica-based synthetic zeolite that often is used in cracking as a cracking catalyst in the oil industry. This provides proof that the MFI zeolite has flexibility. Now this is a different type of situation than looking at a two-fold MOF. This is not a major structural change that we see with MOFs, where the whole cage-like structure can change in its structure, in its design and structure. Now, initially, what you will see, the structure of the MFI zeolite takes on, I'm sorry, this should have been a nice round circle, but this pore is structural, and this produces what's called a straight channel. And if you were to look directly into your screen and look down this would appear to be something like a cylinder. And it takes on this type of a structure here, and you can see the actual channel. Now, originally it had been believed that MFI zeolite did not undergo structural changes at all, and the pore structure did not change during its activity. But Dr. Nakai added argon and did adsorption and structural analysis, and he found that there were actually changes in the pore shape itself. Now, this is not a complete structural change, it's just a change in the pore structure. And as a result, instead of having this cylinder or single channel view, now the structure takes on a shape such as this. Now, this has become much more ellipsoidal, and this is represented by the sinusoidal channel, where originally we would be able to look straight down this single channel. Now we have a sinusoidal type channel. But interestingly, if we, instead of exposing the MFI zeolite to argon and we expose it to nitrogen, there's a further shape change that occurs. And this also produces a sinusoidal channel structure. Now, what's happening here is that this is the original structure, and you can see it's pretty much circular, and we'd be looking down through this channel. And we're going to look at this particular dimension, and this has a dimension of 5.81 angstroms. And when we expose it to argon at 87 K, we find out that measuring along that same axis, that the size has changed to 6.35 angstroms. But then when we expose it to nitrogen, there is a slight change in this dimension, and it decreases to 6.22 angstroms. So the next step is to look at the dimension orthogonal to the one up here. And when we look at that, we see at the basic structure of the MFI zeolite has a dimension of 5.03 angstroms, but then exposure to argon reduces that size to 4.34, and then finally over here to nitrogen. So there is a change in the dimension, but the whole structure of the MFI zeolite is not changing. This is a structural change that I was mentioning in terms of a real structural change. We're not seeing that, we're just seeing a change in this pore dimensions with MFI zeolite. But this was never known before, and it was assumed that no changes would occur. So this is the type of information that can be gleaned by you doing doing adsorption and XRD simultaneously. Now, we've been asked if these types of systems are truly in place and operational, and I just want to give you a couple, just take a minute just to explain and give you a couple of examples of locations where this type of integration of various types of instruments is in place and actually being used. Now, this is a synchrotron radiation powder diffraction that's working with a BEL-MAX at a couple of different locations. This is called Spring 8 in Japan. This is an aerial view of that facility. This is somewhere on the order of 100 to a couple hundred yards in diameter. And this synchrotron is typically used for evaluating atomic physics. But it has an XRD that is used as part of their analysis, and the BEL-MAX system was patched in with that XRD to do powder evaluations. A similar system, but not really attached to the synchrotron, is also installed in Berlin, in Germany, under the auspices of Professor Kaskel. We also have installations with small angle X-ray, and that is patched in together with the BEL-MAX. And this is the same concept of integration that's used with XRD. And this is located at KIST in Korea under the auspices of Professor Terasaki. Now, in this case, because we're looking at a small angle X-ray, and a Bell cryo-stirling system is used as a means of providing the cryogenics for the system, as we described for the combined XRD adsorption BEL-MAX system. The BEL-MAX system can also be integrated with the laser Raman or fluorescence spectrometers. These are installed at Riken under Professor Hyogo, and at ICEMS in Kyoto, Japan, under the control of Dr. Kitagawa. Also in the United States, NIST has a customized instrument, and I do want to mention right away, if you're interested in the system that NIST is using and some of the information and research that they're doing, you might want to visit this website. Now, I know this is going to be very difficult for you to copy, but if you're interested in this particular website, if you want this link, just let Jason know, and he will provide that to you. Now, you'll see this term FACT. And what this means is it's an NIST facility for adsorbent, characterization, and testing. Thus the term FACT. And this is looking at energy. This instrument combination is looking at energy usage and efficiencies and other types of information. In this case, we're looking at binary gas adsorption, both volumetrically and gravimetrically, and also looking at multi-component gas adsorption, again, from a volumetric standpoint, and also using gas chromatography. And this is a photograph of that particular installation. And you can see, based upon this does not require an entire room for installation. So in summary, structural changes as a result of adsorption can be studied during the entire adsorption process with the sample remaining undisturbed in situ. Integration of the BEL-MAX with various instruments and specialized systems is possible, and it's presently in use. So I hope you enjoyed this. There's much more information that we can impart, and giving you some references and names, and we can provide. I'm sure those gentlemen would be more than happy to provide any information, and we do have an expert here in the United States that is well familiar with all these integrated systems. So thank you. And Jason, I'll turn it back over to you.
Yeah, thanks, Dr. Plants. Great. Thank you for the very informative presentation, and I hope you guys found it valuable as well. Just quickly, I just want to go over, introduce Bell's core product line. What we have here on the left is the BEL-MAX. It's a high-performance gas and vapor absorption instrument which measures surface area, pore size, including micropores. 3 samples can be independently measured simultaneously and very accurate with low-pressure measurements. In the middle, you'll see the BEL-CAT, which is a series of key absorption analyzers. They could do TPD, TPR, TPO, and pulse chemisorption. And there's also everything from entry level all the way to high throughput models. And then on the right is a BEL-SORT Mini, which is an entry level system, compact, reproducible. It also has 3 independent samples ports. Here's an overview of the custom systems as we kind of focused on. And here we have the VC pictured to the right, which is a multi-component gas absorption system that is combined with gas chromatography, useful for evaluation of gas storage. And as we mentioned, the BG, a binary gas absorption analyzer that combines volumetric with gravimetric techniques into one system. We have a BEL-RIA, which is a compact fixed blow-fed reactor that can be customized to meet your specific needs. A PVT, which is a direct adsorption isotherm measurement, and it's useful for gas storage and separation. And finally, we have a QCM, which includes a quartz crystal microbalance, delivering high sensitive measurements for materials with low sample mass. It measures the change of mass, which is difficult to do with just a volumetric system of the low mass samples. So some of the next steps. So if you are interested in talking about a BEL system and advancing your research, you could schedule a complimentary consultation with us. We could walk you through it because there is a lot of engineering that goes through with these systems. It'll be a no obligation chat, but just to see if it is feasible, and we could talk about next steps, possibly running data, those types of things. So please email me. You've seen some communication from me as well. Send it to me and we will gladly set that up with one of our technical experts. Thank you for watching. For more information on our entire suite of particle characterization solutions, including BEL instrumentation, visit microtrack.com.